Hello everyone, my name is Clarissa Becker. I'm a PhD student at the Technical University of Compiègne. My collaborators are Pascal Ladeur, Pascal Nicolet, and Frédéric Truyen. And today I would like to show you how considering material and physical variability leads to more robust designs in the context of 3D printed continuous fiber composites. 3D printing enables the manufacturing of complex geometries with fine details and irregular structures. But continuous fiber composites are mostly used in lightweight applications. Therefore, the structural performance matters more than the shape itself. It is important to consider the anisotropic material properties in the design process. A common approach to this is the use of numerical optimization to obtain a load-optimized low-volume structure. Then, the fiber direction can be aligned with the stress field for high structural performance. Here, this is simply along the members of the truss structure. Unfortunately, the physical world is not deterministic, and physical and material variability may occur. A physical variability may be the load on the structure. Instead of acting only in the vertical direction, the force could sometimes act at an angle. Or material variability. Then, for instance, the Young's modulus may locally be lower than the determined Young's modulus of the material. A tool to account for such variability is stochastic modeling, where the variability of a parameter is expressed by statistical means, such as the mean value and the standard deviation. In this context, a research question arises. Are equally optimum structures equally robust to such variability? Using numerical optimization, different minimum volume structures were obtained. Equally optimum here means that the difference in volume between the structures is less than 2%. In total, 6 structures were studied, and the structures clearly contain different numbers of members, and also different cross-sectional areas, as indicated by the line thickness. So the maximum displacement of the 6 structures was studied. The input variability was the variability in the Young's modulus. And the studied output variability was the variability of the maximum displacement. The lower the output variability is, the more robust is a structure. To conduct this study, stochastic modeling was used. The study covered various levels of variability from a low level to a very high level. And indeed, the results suggest that structures with more members are less sensitive to the variability in the Young's modulus. The minimum volume structures used in the study were created using a layout optimization tool. First, the domain is defined as well as the boundary conditions and loads. Then, the design domain is discretized by knots. In this example, only 6 knots, 3 in the width and 2 in the height direction. Then a fully connected ground structure is created by connecting each knot with every other. This ground structure contains all potential members of the optimized structure. The optimization algorithm based on linear programming then determines an optimized configuration of members and also determines the cross-sectional areas. Members under tension are shown in red and members under compression are shown in blue. With a porous ground structure like this, the obtained solution is far from the global optimum. But in case of a finer grid of knots, the fully connected ground structure contains more potential members, and the obtained results are much closer to the global optimum. In this case, a structure with 32 members is obtained, as used in the design study. A straightforward method for stochastic modeling is the direct Monte Carlo simulation. For the truss structures, the procedure is as follows. First, random values are assigned to Young's modulus of each member. In this example, the structure has 32 members, so 32 different values of the Young's modulus are assigned. Then the maximum displacement of the structure is determined by using finite element analysis. Then the first and second step are repeated for a number of n trials. Finally, the variability in displacement is calculated from the obtained mean value and standard deviation of all trials. The significant problem with this procedure is that often as much as 10 to 100,000 trials are needed to obtain results with high accuracy. For each trial, one finite element analysis is used, which makes the direct Monte Carlo simulation costly from a computational point of view. One way around this problem with the direct Monte Carlo simulation is the use of the certain generalized stresses method, short CGSM. The CGSM is based on the assumption that the axial forces in the members, which are here modeled as bar elements, are independent from the input variability, which was the variability in the Young's modulus in this design study. Due to this assumption, it is possible to create a CGSM metamodel, and instead of studying the whole structure, only the CGSM metamodel is studied. As a result, only two finite element analyses are needed to obtain the nominal axial forces in all bars. Then, the displacement for any configuration of the Young's moduli is calculated from the CGSM metamodel. In this step, the procedure of the Monte Carlo simulation is applied for n trials again, but without performing any further finite element analysis. Let's summarize some important advantages of the CGSM. Based on the CGSM assumption, the method is exact for statically determined structures, but it can also have a very high quality when a statically indeterminate structure is studied, as it was the case in the presented design study. The method is valid for low to very high level of variability, and it is suitable for large-sized problems due to the reduced number of finite element analysis. And last, the method can be formulated to study the influence of other material and physical variability on the structural behavior. As I promised at the beginning of the presentation, there is a relevance of this research for the design of 3D printed continuous fiber composites. But therefore, I would like to summarize the findings and then make the link to 3D printing. The first finding of the conducted research is the demonstration that it is possible to study the influence of input variability at a low computational cost. This refers to only two finite element analyses needed by the CGSM. The second finding is that numerical optimization does not necessarily lead to robust structures as an optimization result. This finding is based on the different robustness obtained for the 6 structures to the same input variability. And the third, and probably most important finding, is that structures with more members are more robust to input variability. From this finding, rules of design could be derived. But finally, how does this relate to the 3D printing technology? Physical and material variability is a problem in 3D printing. Material variability exists in mechanical properties such as the Young's modulus, tensile or compression strength, or the strain at break. These can be caused by inconsistencies of the filament material or the 3D printing process itself. Also, physical variability exists. This may be variability in the magnitude or direction of loads, or in the geometry, such as the cross-sectional area or the location of the knots. And variability in geometry can increase in non-planar 3D printing. By using numerical optimization, optimized structures can be obtained, which have a minimum volume or minimum compliance. But these can be sensitive to the variability associated with 3D printing. The use of the CGSM to consider material and physical variability increases the quality of the predictive numerical model, and so can lead to robust optimized structures. Based on the presented research, there is some potential for future research. First is the extension of the CGSM formulation to other material and physical variability, and of course 3D problems. Second is the consideration of beam finite elements for CGSM to represent the physical reality more accurately. Third is the enrichment of the optimization formulation, for instance by including Euler buckling of the structural members. And last but not least is the direct coupling of the CGSM with numerical optimization of the structure. Thank you very much for your attention and interest in our research, and please feel free to contact us if you have questions or you want to collaborate. Thank you.